Hello everyone, welcome to the European Non-Associative Algebra Seminar. Today's talk is by Yanyong from Hangzhou from the University of China. And the title of his talk is Novikov Yang-Baxter, Infinite-dimensionally bialgebras and the conformal bialgebras. Please.
Okay, thank you. Thanks to all the organizer for giving me the opportunity to give such a talk here. Today I will give a talk about Novikov bialgebras and the relationships with infinite-dimensional Lie bialgebras and Lie conformal bialgebras. Okay. This talk is based on the following two works joined with Chengming and Li Guo. In the first paper, we introduced the definition of Novikov bialgebras and investigated the relationship between Novikov bialgebras and infinite-dimensional Lie bialgebras. In the second paper, we give a bialgebra theory of Gelfand-Dorfman algebras and investigate this theory with the theory of Lie conformal bialgebras. Note that Novikov bialgebras are class of Gelfand-Dorfman bialgebras. Okay, and next slide we are introduce the results in the following aspects. First, I will introduce some definitions and motivations. Then I will introduce the definition of Novikov bialgebras and the relationships with infinite-dimensional Lie bialgebras. Then I will give an equivalent characterizing of Novikov bialgebra from the Novikov algebra itself. Then I will introduce the definition of the Yang-Baxter equation. Finally, I will introduce the relationship between Novikov bialgebras and Lie conformal bialgebras. In the end, I will provide two problems. Okay, that's why we call the definition of Novikov algebra. In this talk, we always assume the ground field is the field of characteristic zero. Novikov algebra is a vector space A with a binary operation satisfying the following two equalities. The first one is the left symmetric identity, right? And the second one means the commutativity of right multiplication. A Novikov algebra is also called left Novikov algebra. A right Novikov algebra is a vector space with a binary operation satisfying the right symmetric identity and the commutativity of left multiplication. So it's easy to say that the opposite of a Novikov algebra is a right Novikov algebra. And the cradle of the operator of Novikov algebra is the operator of right Novikov algebra. Novikov algebras were introduced in connection with Hamiltonian operators in the work of Gelfand and Dorfman in 1979. And it also appeared in the work of Blinsky and Novikov in the study of Poisson bracket. There is a natural construction of Novikov algebras given by S. Gelfand in 1979. Let A be a commutative associative algebra and D be a derivation. Then the binary operation defined by A, D, B, it gives a Novikov algebra structure on the vector space A. Because the opposite of Novikov algebra is the right Novikov algebra, so the binary operation A diamond B equal to DAB define a right Novikov algebra. So we can obtain many examples of Novikov algebras or right Novikov algebras. There is a special example. Equip the Laurent polynomial algebra with the natural derivation. Then there is a right Novikov algebra structure on the vector space of Laurent polynomials, right? We need to keep it in mind. The importance of Novikov algebra is also in the relationship with infinite dimensional Lie algebras. Let A be a vector space with a binary operation. Define a binary operation on A times the vector space of Laurent polynomials by the following equality, where A Ti equal to A times Ti. Then A T minus 1 is a Lie algebra if and only if A is a Novikov algebra. This Lie algebra is called the Novikov algebra affinization of A. From this proposition, we can see that Novikov algebras correspond to a class of infinite dimensional Lie algebras. Right? And we can see that because the TI equal to ITI TI plus J minus 1, we have known it defines a right Novikov algebra structure on the Laurent polynomial, on the vector space of Laurent polynomial, right? So this construction can be extended a more general case. This can be a small result of the paper Ginsburg and Kavarov in 1994. Let A be a Novikov algebra, B be a Z-graded. Here we take the Z-graded because in our paper sorry. Okay. Let A be a Novikov algebra and B a Z-graded right Novikov algebra. Then we define a binary operation on A times B as follows, right? Then A times B is a Z-graded Lie algebra. We call that the induced Lie algebra from A and B. Furthermore, if we take B, the right Novikov algebra on the vector space or Laurent polynomial, then A times B is a Z-graded Lie algebra if and only if A is a Novikov algebra. In this special case, it is just the Novikov algebra affinization, right? We hope we can lift this construction to the case of bialgebra. So there are some natural questions. Note that the theory of Lie bialgebras has been well developed, right? Can we use the definition of Lie bialgebras and Novikov algebra affinization to obtain a definition of Novikov bialgebras? If so, can we study it from the point of value of Novikov algebra itself as the classical bialgebra theory? Moreover, we can ask, can we lift the general construction above to contest of bialgebras? Right? We will provide the answers later on. On the other direction, Novikov algebra are closely related with Lie conformal algebras. So we need to recall the definition of Lie conformal algebra. A Lie conformal algebra is a K partial module with a lambda brackets, which define a K bilinear map from A times R times R to R lambda. The elements in R lambda is just the polynomial associated with lambda with the coefficient in the R. The satisfying the following equalities, right? The first one is secular linearity, right? And the second one is skewsymmetric. The second is identity. Lie conformal algebras were introduced by Victor Katz in 1997, which have close connection with vertex algebras and infinite dimensional linear algebras and nonlinear evolution equations. There is a correspondence between Novikov algebras and a class of Lie conformal algebras. Let A be a vector space with a binary operation. Then we equip the free K partial module with a bilinear map. A lambda B equal to partial B circle A plus lambda A star B. Then we can check that R is a Lie conformal algebra if and only if A is a Novikov algebra, and A star B is equal to A circle B plus B circle A. We call R the Lie conformal algebra corresponding to the Novikov algebra. So similarly, the case with infinite dimensional linear algebras, we can ask a similar question. Note that the theory of Lie conformal bialgebras have been well developed by Liberty in 2008. That there exists a similar correspondence between Novikov bialgebras and a class of Lie conformal bialgebras. Right. So in this talk, we will provide answers for these questions. In this talk, we always assume that K is a field of characteristic 0. A is a finite dimensional Novikov algebra, and each Bi in the Z-graded right Novikov algebra is a finite dimensional. Okay, let's begin the main test. Here we needed to introduce the definition of Novikov coalgebra. It is easy to obtain this definition. We can due to the definition of Novikov algebra, right? So a Novikov coalgebra is a vector space A with a linear map from A to A times A, such that the following equality holds. Here tau is just the flip operator. Because A is a finite dimensional, so A delta is a Novikov coalgebra if and only if A star, A star is just the dual space of A. A star is a Novikov algebra. Then we need to give a construction of Lie coalgebras from Novikov coalgebras and the right Novikov coalgebras. In particular, the Novikov coalgebra affinization, right? We should consider the case in the context of coalgebra, right? Because the dual of coalgebra is a Novikov algebra, right? And the Novikov algebra foundation realizes the definition of Novikov algebra. So the first step is needed to find a coalgebra structure on the space of Laurent polynomials whose graded linear dual is the right Novikov algebra of Laurent polynomials. So we needed to do this step. There is an observation. Let C be the Z-graded space of Laurent polynomials, and let A be the graded linear dual. Then the right Novikov algebra product on A can be the induced product from the graded linear dual of any coproduct. This can be easily checked. I give a proof as follows. Suppose that such a coproduct exists, denote that xi, the following sum, right? Then using graded linear duality, we can obtain that xi should be an infinite sum. So it can be defined by a usual coproduct. So what it means, there we need to allow the image of data be an infinite sum, right? So here we need to introduce the completed tensor product. Let C and D be the graded vector space. Then we take their completed tensor product. What means it just means the element in C tensor head D can be an infinite sum. If C and D are finite dimensional, C tensor head D is just the usual tensor product, right? Oh, okay. Then we can introduce definition of completed right coalgebras. A completed right coalgebra is a pair where C is a Z-graded vector space and the data is a linear map satisfying the two equalities. Comparing the usual definition of right coalgebra, the difference is at here we along the image of data can be an infinite sum. Here tensor head data tensor head identity just means that it may act on the infinite sum. Here we present an example. On the vector space of a Laurent polynomial, we define a linear map that B by the following equality, right? One can check that this is a completed right coalgebra. So now we have a right Novikov algebra structure on the vector space of Laurent polynomial, and a completed right Novikov coalgebra structure on the vector space of Laurent polynomial, right? Then we introduce the definition of completely coalgebras. A completely coalgebra is a pair where L is a Z-graded vector space and the data is a linear map satisfying the two equalities. It can be interpreted similarly. Now we can present a theorem in the context of coalgebras. Let A be a Novikov coalgebra. and B be a completely right coalgebra, and L equal to A times B. Then we define the linear map data by the following equalities. Here, the black operation means that we can test data AA and data BB, right? Then we switch the second operation with exchange A2 and B1I alpha, right? Just the exchange the operation of the in the second operation, right? And the third operation, right? Just we exchange the A2 and the B1 alpha, right? Then we can check that L data is a completely coalgebra. Furthermore, if we take B, the completely right coalgebra on the vector space or round polynomial, then L is a completely coalgebra if and only if A is a coalgebra. Consider a bialgebra. Here we also need another definition. A bilinear form on a Z-graded vector space B is called graded if there exists some M belong to Z, such that Bij equal to 0 for all Ij belong to Z, satisfying I plus J plus M not equal to 0. A graded bilinear form on a Z-graded right logical algebra is called invariant if it satisfies the following equalities. Quadratic Z-graded right logical algebra is a Z-graded right logical algebra together with a symmetric, invariant, non-degenerate graded bilinear form. What mean? If we take M equal to 0, the non-degenerate means that for each I, Bi either to I morphic to B minus I, right? In particular, when B equal to B0, it just means B is finite dimensional. It is simply called a quadratic right logical algebra. Okay, now we print an example. On the vector space of round polynomial, right? It has a Z-graded right logical algebra. Then we define a bilinear form on B as follows. Tij equal to delta I plus J plus 1, 0. One can check that it is a quadratic Z-graded right logical algebra. Then by this lambda1, we can say the lambda1 let be a quadratic Z-graded right logical algebra. Let that be the dual of diamond operation and the bilinear form, such that the following equality hold. Then we can obtain that B delta B is a completely right logical coalgebra. So from a quadratic Z-graded logical algebra, we can obtain completely right logical coalgebra. Now we also need to introduce definition of completely Lie algebras. A completely Lie algebra, the definition is similar to the usual definition of Lie algebra. Here we only along the image of delta can be an infinite sum. Now we introduce the definition of a Novikov algebra. Let A be a Novikov algebra. Then we define a star operation A star B equal to A circle B plus B circle A. Let LA RA be the left multiplication and the right multiplication, respectively, right? Define LA star equal to LA plus RA. Then we can see the definition of Novikov bialgebras. Novikov bialgebra is a triple where A is a Novikov algebra, A delta is a Novikov coalgebra, such that the following conditions are satisfied. There are three conditions, right? 1, 2, 3. It seems more complex than the definition of the bialgebra. Okay, now we can present the main theorem. Let A be a Novikov bialgebra and B a quadratic Z-graded right Novikov algebra. Let L equal to A times B be the induced Lie algebra from A and B. Then let that B be the linear form obtained from the quadratic Z-graded right Novikov algebra. And delta be the linear form defined as the case in the coalgebra, right? Then we can check that L is a completely Lie bialgebra. Furthermore, if we take B, the quadratic, the graded right Novikov algebra on the vector space of Laurent polynomials, then the converse also holds. So this theorem answers the second question. Okay, this theorem also called as Novikov bialgebra tensor quadratic right Novikov algebra can produce Lie bialgebras, right? Then I present an example. Let A be the two-dimensional Novikov algebra, right? With the multiplication as follows, and define delta B as follows. This is a Novikov algebra. Then by theorem 2, we can obtain a completely Lie algebra as follows. Here the image of delta can be an infinite sum. Okay, next I will give give an equivalent characterized of Novikov algebras from the Novikov algebra itself. First, we need to recall the definition of representation of Novikov algebra. A representation of Novikov algebra is a triple VLAI, where V is a vector space, LAI from A to the vector space of endomorphism from on V, satisfying the following equalities 1, 2, 3, 4. Note that ALAI is a representation of A, which is called the adjoint representation of A. Then we give a obvious result. Right? Let A be a Novikov algebra. Let V be a vector space, and LAI be such linear forms. Define a binary operation on the direct sum of A and V as follows. Right? Then we can check that V is a representation of A if and only if A the direct sum of A and V is a Novikov algebra, which is called the semi-direct product of A by V. Then we need to introduce some notion that follow. Right? For Novikov algebra, V and V be a vector space for linear map phi from A to end of V. Define a linear map phi star from A to end of V star by the following equality, where the bracket is the usual pairing between V and V star. Then we can give the dual representation of the representation, right? Let A be a Novikov algebra and V be a representation of A. Then V star, LV star plus I star minus I star is a representation of A. So if we have a representation of A, we can produce another representation. We can take the dual representation, right? So the joint representation of a Novikov algebra gives the representation A star, LA star plus I star minus I star. Next, we also introduce the definition of quadratic Novikov algebras. Let A be a Novikov algebra. A bilinear form on A is called invariant if it satisfies the following equality. Here A star C is equal to A circle C plus C circle A. A quadratic Novikov algebra is a Novikov algebra together with a non-degenerate symmetric invariant bilinear form. Here we can easy to see that if this Novikov algebra has an identity element, there are no such quadratic structure. Then we also need the definition of many triples of Novikov algebra. The standard many triple of Novikov algebra is a triple of Novikov algebras, for which as a vector space is the direct sum of A and A1 star, and A1 and A1 star are subalgebras of A. The bilinear form on A defined as follows, and it needs to be invariant. So, by the definition of quadratic Novikov algebra, for many triple, A is a quadratic Novikov algebra, right? Then we can prove the following theorem. Let A be a Novikov algebra, A delta be a Novikov coalgebra. Then there is a Novikov algebra structure on the dual space A star induced by that, right? Then the following conditions are equivalent. There is a many triple if and only if A is a Novikov algebra. So the definition of Novikov algebra obtained from the definition of infinite dimensional Lie algebra. It is reasonable from this theorem. Next, we introduce the definition of a Novikov Yang-Baxter equation. Let A be a Novikov algebra, R be an element in the A tensor A. The equation R diamond R equal to R13 circle R23 minus the following two terms. Here R13 circle R23 can be rated as follows, right? R13 just we can put X alpha, Y alpha in the first position and the third position. R23 we can put X beta in the second position and Y beta in the third position, right? And the here Y alpha, Y beta should take the operation, the circle operation, right? So other terms can be integrated similarly. Such algebras equation is called the Yang-Baxter equation in A. Then we can obtain the following theorem: let A be a Novikov algebra, R be a skewsymmetric solution of the Novikov Yang-Baxter equation. Then we define delta R as follows. Then we can check that A is a Novikov algebra. So from a skewsymmetric solution of the Yang-Baxter equation, we can naturally obtain a Novikov algebra. So natural question is that how to obtain skewsymmetric solution, right, of the Yang-Baxter equation. Here we study the operator forms of the Yang-Baxter equation. For a finite dimensional vector space A, there is the isomorphism, right? A times A is isomorphic to Hom A star A. So they can set the element R to TR in the Hom A star A. That way, that can convert the Yang-Baxter equation to an equality associated TR in the Hom A star A in the vector space, right? In this vector space. So there is the following result: let A be a Novikov algebra, R be a skewsymmetric. Then R is the solution of the Novikov Yang-Baxter equation in A if and only if TR satisfies the following equality. This motivates us to give the definition of all operators. Let A be a Novikov algebra, V be a representation, a linear map, T from V to A is called the O operator on A associated with the representation if T satisfies the following equalities. So in the theorem 5, the equality means that TR is an operator associated with the dual representation of the adjoint representations, right? Then we also have the following results. We can obtain skewsymmetric solutions of the Novikov Yang-Baxter equation from all operators. Let A be a Novikov algebra, V be a representation. Let T from V to A be a linear map, which be identified with RT belong to A times V star. Then we can put it in a big vector space. It's just the semi-direct sum of A and its representation V star, right? Put it in a big vector space through the isomorphism. Hom VK is isomorphic to A times V star. Then it is to check that R equal to RT minus tau RT is a solution of the Novikov Yang-Baxter equation in the semi-direct sum Novikov algebra if and only if T is an operator on A associated to this representation. So if we wanted to find skewsymmetric solutions of Novikov Yang-Baxter equation, we can find all operators, right? Then a natural problem is that how to find the natural all operators, right? Then we here we introduce the definition of pre-Novikov algebra. A pre-Novikov algebra is a triple where A is a vector space with two binary operations, triangle left, triangle right, satisfying the following equalities. That is four equalities. Right? It seems complex, but here we have some constructions. Right? Recall a bialgebra is a vector space A with a binary operation satisfying the following equality. Then we take a derivation D on a bialgebra. Then we define two binary operations, triangle left, triangle right, as follows. We can check that this algebra is a pre-Novikov algebra. So we can construct pre-Novikov algebras from bialgebras with derivations. Right? Here we also need some notation. For pre-Novikov algebra, define linear maps L triangle right, triangle left, as follows. Right? Then we give a pre-Novikov algebra. Then we define the circle binary operation as follows. It is equal to x triangle left y plus x triangle right y. It really defines a Novikov algebra. This Novikov algebra is called the associative Novikov algebra of the pre-Novikov algebra. Moreover, A L triangle right, R triangle left is a representation of A, and the identity map is an O operator on A associated with the representation. So from pre-Novikov algebra, we can obtain a natural operator, right? Then associated with the results given as before, we can obtain this theorem. Let A be a pre-Novikov algebra and A circle be the associated Novikov algebra. Then R is a skewsymmetric solution of the Novikov Yang-Baxter equation in the Novikov algebra, in the semi-direct sum Novikov algebra, where E1 and En is the linear basis of A, and E1 star, En star is the dual basis of A star. So from pre-Novikov algebras, we can obtain many. We can obtain Novikov algebra. Next, I will introduce the relationship between Novikov algebra and the Lie conformal algebras. Here we need to recall the definition of Lie conformal coalgebras. A Lie conformal coalgebra is a K-partial module with a K-partial module homomorphism such that the following two equalities. Where the K partial module structure on R times R is defined by partial X on A times B equal to partial A times B plus A times partial B. A Lie conformal bialgebra is a triple such that R is a Lie conformal algebra, delta is a Lie conformal coalgebra, and they satisfy the co-cycle condition as follows. Where A lambda delta B equal to sigma A lambda B1 times B2 plus B1 times A lambda B2, if delta B equal to the sum of B1 times B2. Okay, next I will give the correspondence between the bialgebra and the class of Lie conformal bialgebras. Let R equal to K partial A be the Lie conformal algebra corresponding to a Novikov algebra. Let delta from A to A times A be a linear map. Then the triple is a Lie conformal bialgebra with the K partial module homomorphism given by delta A equal to partial tensor identity map delta A minus the flip operator acts on partial tensor identity map delta A if and only if A is a Novikov bialgebra. So so we can construct a Lie conformal bialgebras from Novikov bialgebras, right? In fact, we prove there the following commutative diagram. The first line is shown before, right? And the second line, this result have been known before. Then we check, we show that the free-Novikov algebras correspond to a class of left symmetric conformal algebras. And all operators on Novikov algebras also correspond some all operators on the corresponding Lie conformal algebras. And the solution of the Novikov Yang-Baxter equation also corresponds a class of solutions of the classical conformal classical Yang-Baxter equation. And we also prove that the diagram are commutative. Finally, I provide two questions. And we shown Novikov algebra tensor quadratic right Novikov algebra can produce completed Lie algebra, right? There are also some similar results. For example, Lie algebra tensor Frobenius algebra can produce complete Lie algebra. This is known. So I think there may have a general result from the point of value or operator. The second one is that, as we know, look at algebra correspond to a class of infinite dimensional completed Lie algebra, right? And the algebra also corresponds to a class of Lie conformal algebras. So Lie conformal algebra and the completed Lie algebras, there should be some relationship, right? So what's the relationship between Lie conformal algebras and the completed Lie algebras? Okay, that's all. Thank you for your attention.
Thank you very much for the talk. Other questions? There is a question in the chat. The Manin is asking for other examples of solutions for some Yang-Baxter questions. Can you see the question in the chat?
Sorry, I can't hear your voice.
There is a question in the chat. Can you see it?
Using Yang-Baxter equation.
Yes, and why be some kind of Yang-Baxter question? Do you have other solutions?
Sorry.
Equations?
I don't know. I understand your meaning. Here I have
there is a question in the chat. You can check in the chat.
Yeah, the question in the chat. Can you read it? The question is about other solutions for some kind of I don't know N by B. What does it mean? Some kind of question. Which type is it? Multiple. And what does N stand for in this relation?
Okay, so
okay.
Yeah, so in the chat there is a question.
Okay.
The chat. You look at the chat.
Other examples of solutions for the Yang-Baxter equation. We have no other examples. We in this paper we only have the solutions of obtained pre-Novikov algebra. For example, from half algebras. Maybe, but I don't know. Thank you.
Other question?
Yeah, in principle, right? In principle, all operators will give solutions of Yang-Baxter equation, but then first one need to construct all operators. Yeah.
Yes.
So, yeah.
There's one more
there is another question in chat.
Can you please provide more explanation for the Yang-Baxter equation? This is the definition, right? The definition of the Yang-Baxter equation is just this equality, and I think this definition is can be interpreted, right? The Yang-Baxter equation is also is related with the classical Yang-Baxter equation. This is the result is I give in the end. In this proposition, right? Just this proposition means that let A be a Novikov algebra, B be a quadratic Z-graded right Novikov algebra, and L equal to A times B. Then suppose that I belong to A times A is a skewsymmetric solution of Novikov Yang-Baxter equation A. Then for basis EP consisting of homogeneous elements of B and its homogeneous dual basis P associated with the bilinear form. Then the tensor element IL belong to A tensor hat L is a skewsymmetric complete solution of the classical Yang-Baxter equation in L. Furthermore, if we take B equal to the quadratic Z-graded right Novikov algebra on the vector space of Laurent polynomials, then IL equal to such infinite sum is skewsymmetric complete solution of the classical Yang-Baxter equation. If and only if I is a skewsymmetric solution of the Novikov Yang-Baxter equation. So from this proposition, maybe we can interpret the Yang-Baxter equation from the point of value of classical Yang-Baxter equation. Right.
Okay, thank you for your explanation.
Thank you.
More questions? Okay, if not, let me thank the speaker again.
Thanks.
And so thank you very much for your talk.
Okay.
I guess we can stop at this point.
Okay.
So I wish you a good week to all of you. See you next Monday.
See.
Okay.
See
Thank you. See you.
Thank you.